So probably if you've seen slopes of or anything about the slope of a line before, it comes usually in the form of a formula for how we get it. So we'll talk about that, but we're also gonna look at just the general definition of a slope, because that general definition can kind of help us with some of the like the special cases, like vertical lines and horizontal lines and things like that. So let's look at just a graph. We'll start with. So if I've got the graph of a line, let's say, I didn't even go through the points I said I was going to go through, but that's okay. We'll do that guy. And then we'll do one more, maybe. So when it comes to lines, there's sort of two things you need in order to know everything about a line. One is kind of an anchor point. So you need to know one point that's on the line, which is usually people think of the y-intercept as sort of that anchor point as far as like telling us where the line is situated on the graph. And then the slope of the line tells us how the y values change. So essentially it tells us how steep the line is. So we could take that blue line, right, and create all sorts of other lines with the same steepness that are higher up or higher down on the plane. Or we could take any line that goes through that single point and make it a different steepness to create a different line, right? But there's only one line that has the same steepness as that blue line and goes through that same y-intercept. So once we know one point on the line, that situates us on the plane, and then the steepness tells us really what the line itself looks like. So the slope of a line, when we talk steepness, in everyday life, the best example I can give you of slope is like the grade of a hill. So when you're driving like on a pass or something and it says that there's a 6% grade, what that means is that for every 100 feet that you drive horizontally, your elevation goes up or down, depending on if you're going up or down, by 6 feet. So the ratio of your vertical change to your horizontal change in distance is 6%, or 6 over 100. And so the slope is a ratio. It's not like a set number, and it has nothing to do with where we are on the graph. It's just telling us how steep that line is. So the formal definition of the slope of a line is, so the slope of a line is the change in the y value resulting from a 1 unit increase in the x value. Physically, what we're saying is as you move 1 unit to the right on the line, whatever happens to your y value, that number is going to be your slope. So for instance, on our black line here, if I were to start at this point and move 1 unit to the right along the line, that gets me to this point, right? What happened to my y value? By how much?
4.
2?
2. Well, subtracting 6.
Oh, I see what you're saying. So from this first point to this second point, so as we're moving from the left point to the right point, our x value changed or increased by 1 unit, right? Because we moved right to the 1 unit. And then our y value increased by 2. And so the slope of this line is 2 because when I move to the right along the line 1 unit, every single time my y value goes up by 2. And that has nothing to do with where we are on the graph, right? So like I could be down here, and if I move along this line in such a way that my x value increases by 1 unit, notice my y value is also, again, increasing by 2 units. So the slope is a property that has nothing to do with the point that you're at on the line. It just tells us how steep that line is. So just like if you're driving at a 6% grade, like it doesn't matter how far you drive along that hill, right? The steepness doesn't change based on where you are on the hill. We call the slope a unit rate because it tells us the change in one value corresponding to a 1 unit change in the other value. And because it's a ratio, we don't even have to just move 1 unit. We can simply take the change in y divided by the change in x to find that unit rate. So if I were to start at this point down here and go all the way to, oh, I don't know, how about this point right here? So that's clearly more than 1 unit change in my x value. It is, in fact, 1, 2, 3, 4, 5, 6 units to the right. And then what's the corresponding change in y? They're little squares, they're hard to count, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You guys see 12? And so the ratio is the same, right? If I say the change in the y value over the change in the x value, well, the change in my y value is a positive 12 because we're going up 12. The change in my x value was a positive 6 because we were moving to the right 6. And again, that gives me the same exact slope. So we can use any points on our graph to determine what the steepness of it is just by finding that ratio of how the y value is changing compared to how the x value is changing. Does this make sense?
So even though the 6 is in the negative x value, it doesn't matter.
Right, so slope has everything to do with how
Direction.
the value is changing. So if I'm starting at a left or a more left point and moving to the right, then that's a positive change. Yep.
If you went to the left from there, it was negative.
That would be a negative change, yes. In general, I always go to the right because I like to think of only 2 directions instead of 4. So if you always think of moving to the right, then you can think of a positive slope as going up and a negative slope as going down. Otherwise, you have to think left up, left down, left right, or right up and right down, like 4 different combinations, right? So if you always think of moving to the right along your line, any line that's going up as you move to the right is increasing and has a positive slope, and any line that goes down as you move to the right is decreasing and it has a negative slope. So let's look at this blue one. I'm going to just pick a couple points here. So the first thing to notice is that it would be super inconvenient of me to find the slope of this line by thinking of my formal definition of moving 1 unit to the right, because if you move 1 unit to the right I'm going to like cover it up if I even try to move 1 unit to the right. But that's like not a very convenient change in y to count, right? Because it's like some fraction of 1. So in cases like that, it's especially useful to use this fact that we just need a ratio, so I can change my x value as much as I want and just divide the change in my y value by the change in my x value, and that'll give me my slope, so that we don't have to count these little tiny fractions to correspond to a single unit change in x. So I can go from 0.6 to 4.7, and that's a change of how much in my x value? 4. And in my y value? 1. Good. So then in that case, the change in y over the change in x is 1/4. And we typically leave them as fractions rather than decimals. One reason for that is that it's a lot easier to visualize it as a fraction, right? If you think of the numerator as how your y value is changing and the denominator as how your x value is changing. So let's generalize this whole thing. And say the slope of the line passing through the points x1, y1. And those are just subscripts. They just serve as labels so that I can separate one x value from another or distinguish one x value from another. Those subscripts don't do anything mathematically. And x2, y2. So we've got some line, and we've got a couple points on it. Ooh. This one we're going to call x1, y1. And this one down here we're going to call x2, y2. And just like we did when we were just counting them off the graph, we're just going to find the difference in our y values and the difference in our x values. Went a little too far there. Well, to find the difference in my y values, so we say is given by m equals, so the slope is typically represented by m, and it is the change in the y values divided by the change in the x values, just like we saw. So to find the change in my y values, well, if you're on an elevator and you start at floor 3 and you end at floor 9, what's the change in your elevation? Floor 3 to floor 9. 6, right? Which we can get just by subtracting our beginning position from our ending position. And so the change in our x values is just going to be, in the y values is just going to be the difference in the two y values. So the second y value minus the first y value. So y2 minus y1. And then the same is true with your x values. To find the difference in the x values, you just subtract your beginning position from your ending position. So this is going to be x2 minus x1. And the order of those really doesn't matter. Like the whole 1 and 2 thing is just a way of distinguishing the 2 points from one another. Like I could have switched that and done y1 minus y2 over x2 minus x1 and gotten exactly the same thing. The only thing that's important is that you're consistent. Once you decide what your first point is and what your second point is, you can't change your mind when you switch from the y's to the x's. So these two pairs have to come from the same point. So if you look vertically, the x and the y should be from the same ordered pair. So let's do a couple calculations to see this. I don't need that guy. Cut. So let's find the slope of a line passing through like, where is it? There it is. -1, 3, and we'll do 1, -4. So again, we're just going to use that formula. So m is equal to, so I'll just choose the second one written to be my second point and the first one written to be my first point. So my second y value minus my first y value is going to be the change in my y values. So that's this guy and this guy. And then divided by my second x value minus my first x value. So that's this one and this one. Again, if you check, notice that those two numbers come from the same point, right? 1, -4, and that my other point is -1, 3. If I had swapped either the top or the bottom, then they wouldn't have aligned. So vertically, they wouldn't have come from the same point. So that's always a good thing to check that you haven't flipped those guys. And so simplifying gives me -7 over +2, so my slope is -7/2. Which means that on this line, if starting at any point on the line, if you move to the right 2 units, the corresponding change in y would be down 7 units because that's a negative slope. So that means we're going right and down as opposed to right and up. Questions so far?
X
Yes.
is always positive, you do.
Yeah, I mean, you can end up with a negative
But
x.
that's where you were going before when you were like.
But yeah, but if you always think of like physically on the graph, if you think of x as being positive, then it's a little easier to not have so many signs to manage. You guys want to try one real quick?
So why wouldn't 3 be a positive? Why wouldn't you add it to 4 instead of a -3?
So because
Positive up there.
we're finding the change in our x values, so we're subtracting the 2 x values. And the signs can get a little tricky when you have negatives. Notice that I put that -1 in parentheses. That's very helpful as far as not getting the minus sign and the negative sign mixed up when you do the subtraction. So always put those negative numbers in parentheses. So here's one for you guys to try. So find the slope of a line. I don't know why I'm saying a line. It's the line. Passing through three, 4, and -6, 10. Let's say the cost, I think we did this one last week, to rent a restaurant for an event is $40 for setup, and $16 per guest. So let's write an equation. For, we'll call it C, the total cost to host X guests. So my total cost we're calling C. How would you calculate your total cost? What do you have to pay for here?
You have one set up and then how many ever guess.
Mm-hmm. So if I was going to calculate how much I had to pay, we'd start with
40 plus 16 max.
uh-huh. So we'd start with that $40 that I have to pay no matter what, and then 16 times however many people are going to attend. So which one of those numbers tells me the change in price when I increase the number of people by 1? Mm-hmm. So the change in price, or cost, I guess we're calling it, when the number of guests is increased by 1. And the answer to that is 16, right? Every time I add another guest, my total cost is going to go up by 16. Notice that that question I wrote right there is just the definition of the slope of a line, right? It's the change in your y value, in this case it's C, but the change in the output of your equation when x increases by 1. So when we move to the right by 1. So that means that this 16 right here is the slope of the line. And when your equation is in this form, that will always be true because every time we change x by 1, every time we increase x by 1, that's like adding another 16, right? So you do 16 times 1, and then 16 times 2 is going to be 16 more. 16 by 3 will be 16 more than that. So every time that x value is increasing by 1, whatever that coefficient is, that's how much your y value is going to be changing. And so we call this form of a line slope-intercept form of a line. It's y equals m times x plus b. And in this form, the thing you want to notice is that the equation is solved for x, or sorry, for y. So before you start thinking about anything we're about to say as far as what the slope of the slope-intercept form tells you, you have to make sure that your equation has y by itself on one side. So once we get y alone and we simplify the other side, then we have this form. And in this form, the coefficient, so the number that's being multiplied by x, is the slope of your line. And then, well, b, notice if I were to plug 0 in for x, y would be equal to b, right? And so what did you guys learn on Thursday about the point where x is 0? What point is that?
Origin.
So if they're both 0, that's the origin. But if you're just at some point where the x value is 0, what do we call that point?
The y-intercept.
Yeah, it's the y-intercept, right? It's the point that's on the y-axis. And so because plugging 0 in for x into this form will always give me b, we can say that the y-intercept of this line is 0b. And so this form is pretty convenient because remember we started out today saying that the two things you need to know in order to know everything about a line are like an anchor point, right? So a single point on the line that kind of like orients you on the plane, and then the steepness of the line. And this form gives us both of those things just right in the equation without having to do any calculations. So it's convenient in that sense. Let's use this to graph a few lines. So we can use the information about the slope and y-intercept to actually graph the line so that we don't have to like make tables, right? Because one point is already given to us, and then the slope kind of gives us directions on how to get to another point from that first point, because it tells us what the change in x and what the change in y have to be from a single point on the line. So let's do a couple graphs. Any questions just on the form itself before we move on? Good. Sometimes when you're really quiet, I don't know if it's because you have no idea what I'm talking about or if I'm like boring you to death. So if you have no idea or you have questions, definitely speak up. Good? Okay. So let's graph y equals 2x minus 3 using the slope and y-intercept. One thing you guys may have noticed on my math lab over the weekend is that if they tell you how to graph the line, they're actually checking the points that you use, not just that the line is correct. So like if they said graph using the intercepts, the 2 points that you have to use to graph the line have to be the intercepts, because the problem's not just checking that you know where the line is, it's also checking that you're able to find the intercepts. So the same is true when you're asked to graph using the slope and y-intercept. They'll check to make sure that one of the points is the y-intercept, and then the second point is the point you would get to using the slope from the y-intercept. So I just wanted to point that out because it can get a little frustrating. So our slope is what? 2, good. And then our y-intercept is 0, -3. Again, that b, so the constant term in the equation tells us the y-coordinate of our y-intercept. And then the variable term tells us what our slope is. So in order to graph the line using this information, we're going to start at the point we know, which is our y-intercept, so 0, -3, which is right here. And then our slope tells us that from any point on our line, if we move to the right 1 unit, our y value will increase by 2. And so from the point that I know, so from my y-intercept, I'm going to move to the right 1 unit, and then the slope tells me that my y-coordinate has to increase by 2 units, which gives me a second point on my line. So that slope sort of serves as instructions of how to move from one point to another. And if you like to, you could make like a whole little staircase with like a bunch of points on it, but really you just need the 2. So now we have everything we need to graph the line. So I did not even go through that point. Okay. It's a pretty bad line, but we're going to call it straight. It's easier imagination. Did that make sense how we use those? Let's do another one. Let's graph do 4x minus 3y equals 9 using the slope and y-intercept. So when the equation's in this form, which we call general form of a linear equation, notice that my y is not by itself. So we are not in slope-intercept form. Typically, when the equation's in this form, I use just the intercepts to graph because they're fairly easy to find. So it's fairly simple to put 0 in for one variable and solve for the other when it's in this form. However, if I did that, I would get some nasty fractions in this case. If I put 0 in for y and divide both sides by 4, I get y equals 9/4, which isn't super convenient to graph. And so instead of using my intercepts, I'm going to solve this equation for y. And this is where what we did last week when we solved for one variable in an equation that had multiple variables, where that's going to come into play. I want to get y by itself, and then this equation will be in slope-intercept form. So we've got 4x, my pen's lagging, 4x minus 3y equals 9. And I'm going to start by subtracting 4x from both sides. So we've got negative 3y, come on, buddy. There we go. Equals, and you can write it as 9 minus 4x. Some people really like that variable term to be first so that it looks like mx plus b, right? If that's the case, then you would just write this as negative 4x plus 9. Right? So just as long as your 4x is negative and your 9 is positive, it doesn't matter the order that the two terms are in. And then we'll divide both sides by negative 3. So last week when we did this, we said, okay, this gives me y equals the entire right side divided by negative 3. Which is fine, except this still isn't slope-intercept form because slope-intercept form has like the two separate terms, right? It's difficult to pick out what my m and my b are when I have a big fraction like this instead of two separate terms. And so it turns out that division works just like multiplication. You can distribute the same way we distribute multiplication. So if I multiply by a sum like 2 times 5x plus 6, we know that we can distribute that multiplication to each individual term. Division works the same way. If you're dividing a sum, like negative 4x plus 9, by a single number, you can divide each term by negative 3 individually. Because dividing by negative 3 is really the same as just multiplying by negative 1/3. And so it's going to, I could distribute that if I did it as multiplication, right? So this is the same as y equals negative 4x over negative 3 plus 9 over negative 3. So that only works if the addition or subtraction is in the numerator and there is a single term in the denominator. This is not a thing you can do. Like, that does not work. So let's simplify. This gives me y equals positive 4/3 times x, and then minus 3. And I brought that x out of the fraction just so that I have a coefficient, so I have a single number times x as opposed to having x incorporated into that fraction. So far, so good? Okay, so now let's graph it. Our slope is negative, no it's not. Our slope is 4/3. And our y-intercept is 0, negative 3. So again, we always start with the point that we know. So in this case, 0, negative 3 is a point that we know is on the line. And then instead of going to the right one and up 4/3, which could be kind of tricky because of the fraction, remember that that slope is a ratio of the change in the y over the change in the x. So we can think of this as our change in y and this as our change in x. And so from my point, I'm going to increase my x value by 1, and then I'm going to increase, not 1, I'm going to increase my x value by 3, and then I'm going to increase my y value by 4. So my change in x is a positive 3, my change in y is a positive 4, and that gets me to my second point right here. Any questions on that process? Okay, I'm going to have you guys do one. So let's graph 4x plus 5y equals 10 using the slope and y-intercept. So again, notice that it's not in slope-intercept form yet, so you're going to start by solving that equation for y. Okay, so did we all get there for our equation? Negative 4/5 x plus 2. And if you had that written as 2 minus 4/5 x, that's totally fine, same deal. And so our slope is what?
0, 2.
So that's our y-intercept. Perfect, no, you're fine. We need that too.
Just did that first.
And then you guys said the slope was?
Negative 4/6.
Yeah, good. So we've got 0, 2, that's our point. And then here, notice we have a negative slope. So we're always moving to the right. Negative is down, positive is up. So I'm going to move to the right 5 units for my change in x. 1, 2, 3, 4, 5. And then I'm going to go down 4 units for that negative change in y. So 1, 2, 3, 4. You could also go left and up, but again, I find it simpler to think of always moving to the right and then just go up or down instead of remembering like all 4 combinations of ups and downs and lefts and rights. Look good? Okay, let's talk about some special cases, and then we'll do some applications. Did you guys talk about horizontal and vertical lines on Thursday? Okay, so let's look at a horizontal line first. So let's graph y equals 3. So we don't need anything special to graph this. We know that y equals 3 is just the point, or sorry, the line that has all the points with y value of 3. And so I'm just going to pick a couple points with y value of 3 and draw a line through. And that gets me this horizontal line. What is the slope of this line? Yeah, it's 0. And we can see that a few different ways. One thing we can think of is that this is like y equals 0x plus 3, right? Because there's no term in there that contains x. There's no variable term. So we could put that variable term in there as long as it's just equivalent to 0. So we see the slope here as 0. For me, the simplest way to see it is just to remember that formal definition of the slope, that it's the change in your y value that occurs when you move to the right 1 unit on your line. So if I start at some point on this line and I move to the right 1 unit, what happens to y? Nothing. It doesn't change at all, right? It changes by 0 units. So when we move to the right on, so when we move to the right 1 unit, that gives us a 0 unit change in y. And then we can also look at it in terms of a couple points. So if I pick 2 points on this line, 1, 2, 3, 4. So negative 4, 3, and 5, 3. I can use my formula for slope to calculate the slope of the line. So m is equal to 3 minus 3 divided by 5 minus negative 4. So 0 over 9 is equal to 0. Very good. So looking at all the different ways that we can define slope, we end up with a slope of 0 in every different way of looking at it, right? So this is sort of the simpler one. Let's talk now vertical lines. A vertical line is a line where all the x values are the same. So let's start with graphing. We'll do x equals 5. There it is. So again, this is just a vertical line, right? We have all the points with an x value of 5. So 1, 2, 3, 4, 5. It's right here. Well, if we look at our equation, we run into a problem trying to find the slope because this equation is not in slope-intercept form, and it cannot be written in slope-intercept form because there's no y. Remember that if your equation's in slope-intercept form, it has y by itself on one side of the equation. And because there is no y in this equation, there's no way for me to get y by itself on one side. If I were to try to do what I did with the last one and say, oh, this is the same as 0y plus x equals 5, like that's true, but in order to solve that for y, I would have to divide both sides by 0, right? And I can't do that. And so there's just no way to put this in slope-intercept form, which means the equation's not going to give me my slope. So let's look instead at that formal definition. So even if you guys haven't drawn this, I don't care how nice your picture is, but just draw a vertical line real quick. Like it doesn't even have to be on a plane, just any vertical line. Okay, I want everybody to put their pencil point down on any point on their line and move right 1 unit while staying on the line. That is impossible, right? And so if I ask you what happens to y when you move right 1 unit, the question itself does not make sense, right? Because you can't talk about what happens to y when we move to the right 1 unit if we can never move to the right 1 unit, right? So it's impossible to increase x by 1 unit. So we can't talk about what happens to y when we do it. So the slope, well, I shouldn't even say that. Vertical lines have no slope. In mathematics, when we talk about, or when we ask a question that doesn't make sense, so the premise of the question doesn't fit, much less being able to figure out the answer to it. So when the question itself does not make sense, that's where we're in a situation where something is undefined. So there's no mathematical definition that will fit the slope of this line because we can never move to the right 1 unit, and therefore our definition doesn't even, the premise of our definition doesn't make sense, which means we can't reach a conclusion. And so vertical lines just simply don't have a slope. Notice that's very different than having a slope of 0, because when we have a slope of 0, the premise of the question makes sense, right? We can move to the right 1 unit. We just reach the conclusion that y doesn't change when we do that, as opposed to not even being able to move to the right 1 unit, and so we can't talk about what happens to y. And so having no slope and having a slope of 0, they're two different things, because 0 is actually a number. This is saying there's no numerical value that will define our slope in this case. So again, we can look at this kind of in all the different ways that we've talked about. We can look at a couple points as well.
Would a slope of 0 look different?
Yes, that's a slope of 0.
That's right.
So slope of 0 is when you can move left and right, but you don't go up or down. And slope, or no slope, is when you can't move left or right at all. So if I have 2 points on this line, let's see, 5, -4, and 5, 1, and I attempt to find the slope, then we've got m equals -4 minus 1 over 5 minus 5, which gives me -5 over 0. And again, mathematically, it is impossible to divide by 0 because you can't take something and divide it into 0 pieces, right? If you have a pizza and a knife, there is no way to cut that pizza into 0 pieces because the pizza itself is 1 piece, and every time you cut it, you get more, right? So it's impossible to divide something into 0 groups or pieces. And so this is undefined. And so any way we look at it, the slope of a vertical line just doesn't make sense. It has no numerical value. So one of the things to keep in mind as far as actually working with these guys is when you're asked to graph a line. Some people get really stuck in using the slope and y-intercept because it's a pretty convenient way to graph a line. But remember that if you have no y value in your equation, then you're going to have to kind of just know that's a vertical line because there's no slope to use to graph the line. Does that make sense? Okay. What time is it? Oh, we're doing good. Okay. Let's talk applications. So slope is also known as rate of change. So we said the slope is like a unit rate, right? It's a ratio of the change in one thing to the change in the other. So imagine that we have some situation like you are at mile marker 253 when you begin a trip. And mile marker 553, 3 hours into your trip. For our purposes, we're going to pretend that we go exactly the same speed all the time. We set it on cruise or something so that there's no variation. I'm going to ask, what is the rate of change in distance with respect to time? So what I'm really asking here is just how fast you drove, right? We're asking for the change in the distance divided by the change in the time, which we all know is just your speed. But notice the wording, because this is the wording that will come up on all these problems. So the thing that is changing, this is your y value. So when we say rate of change in distance, we're saying our distance is changing. And then when we say with respect to, that's our x value. So that wording is just saying, how is my distance changing as my time increases by 1 unit? So all we're doing is finding the slope of a line. Through, well, we've got 2 points here. When we begin the trip, our time is 0, and that corresponds to mile marker 253. So that's our location. And then 3 hours into our trip, we're at mile marker 553. And so we've got our x values and our y values. And now we're just finding the slope. So 553 minus 253 over 3 minus 0. That gives me 300 what? So what am I measuring with my y values? In terms of units.
Distance.
Yeah, so 300 miles divided by 3, what? What are my units there? Hours, very good. So in order to write a rate of change, we want a single number, and so we want to divide the numbers. So 300 divided by 3 is 100. And then our unit, we're going to write as a single unit. It is the units on the top, and then we use the word per, which represents division, and then the units on the bottom. So our unit on our rate of change is miles per hour. So that last step is important. You want to go from dividing a certain number of miles by a certain number of hours to getting a single number, and then our single unit is this entire thing right here. So just like when we measure speed, we measure it in miles per hour, right? We don't say, oh, I drove 500 miles in 3 hours when somebody asked how fast. That's really fast. How fast we were driving, right? We say, I drove this many miles per hour as a single unit. And so that's how our rate of changes are going to work. And this is one that we're fairly familiar with because we calculate speed on a semi-regular basis, or at least talk about it. But all the other rates of changes that we talk about, we're going to approach in exactly the same way. You just want to remember that you're essentially just finding slope, but with units. So let's look at a couple more. So in the year 2000, 23.2% of adults smoked. In the year 2007, only 19.8% of adults smoked. So we want to find the rate of change in the percent of adults that smoked with respect to time. One good hint if you find yourself getting mixed up about your X's and Y's is that 99.5% of the time, if there is time involved, it will be your X value. Because we always think of the X value as moving, like going in the positive direction, right? And time can only go forward. It's the one thing that only goes one direction. So if you are unsure at all about which one should be your X value and which one should be your Y value, if there are years involved or like times of day or whatever, that's always going to be your X value. So, but again, in the wording, we can also see it. So the thing that's changing, so rate of change in, so whatever is changing, the percent of adults, that's our Y value. And then whatever it is changing with respect to, that's your X value. So it's changing with respect to time. So that's going to be my X value. And then, just because you're probably going to see this in your homework, I should do this. Let's say let X be the number of years since 2000. So quite often we set like a starting point rather than starting at the year 0 because those are annoying numbers to work with and nobody cared who smoked in the year 0. So we just kind of shift this whole thing up by saying that instead of in the year 2000, instead of my X value being 2000, I'm going to make my X value 0. And then measure everything from there. So we're just selecting a starting point that makes sense in terms of the problem. So my points are going to be 0, 23.2, and 7, 19.8. One thing about this that's a little bit tricky is the use of the percentages. So last week we did problems involving percentages. Here the percent is just a unit. Like it's the unit that we're using to measure how many people are smoking. So we're not doing anything mathematically with the percentage as far as like changing it into a decimal or anything like that. It's just a unit. So just like if we were to measure like money in thousands of dollars, the thousand is part of the unit and doesn't have to be part of the numerical calculation. So we're going to calculate our slope. M equals 19.8 minus 23.2. And then change in x is 7 minus 0. So what is that? Like 12 minus 8 is 4. 12 minus 9 is 3. So negative 3.4 over 7. And the units in my numerator are percent. And the units in my denominator are years. So we want to get a single number here. In these application settings, it's totally appropriate to just use a rounded decimal if necessary. So I would do 3.4 divided by 7 and round that to the nearest, I don't know, we'll do like 1 digit. So 3.4 divided by 7. This is what, 4. So I'm going to do 8 times. So that's about 0.5. So we'll say negative 0.5%. I don't know where that P came from. Per year. What does that negative mean? Like, is there like a negative number of people? Right, so since this is about change, it's not like how many people are smoking. The rate of change has everything to do with change. So if it's negative, all that's saying is that the percentage of adults that smoke is going down as time passes. So every year, approximately, or the ratio of people, or the percent of people that smoke goes down by about 0.5% every year. So the percent of adults that smoke decreases by 0.5% per year. And so notice I didn't put the negative when I wrote the sentence because I used the word decrease instead. So it's sort of an either or thing. If you say it's decreasing, it decreases by a positive amount. But the change itself is in the negative direction. So when we calculate it, that's what we get. Okay, here's one for you guys to try. Oh, I don't want to do that. Let's do this one. A bricklayer, sorry, layer began working on a wall at 7 a.m. And by 11 a.m., he had laid. It seems weird. It makes me think of him like lay eggs. We'll say used. What is it? Nothing perverted about egg laying, but bricklaying's a little bit weird. He had used 300 bricks. I feel like that is extremely quick, but find the rate of change in bricks used with respect to time. Where X is the number of hours past midnight. So we're just saying we're starting our day at 12 a.m. as we normally would. So at 7 a.m., that's an X value of 7. Our times are 7 and 11. How many bricks has he used at 7 a.m.? 0, good. And then how many bricks has he used at 11? Good. So now we've got our 2 points. We've got our slope is 300 minus 0 over 11 minus 7. Our numerator is in bricks. And if you did that the other way, if you did 0 minus 300 over 7 minus 11, that's totally fine. You end up with the same thing because it just swaps the signs on both the top and the bottom. So you either have a negative divided by a negative or a positive divided by a positive, both of which will get you a positive slope. So that order isn't important. And then 11 minus 7, what is that, 4? And that is measured in hours. And so we start with the numerical part. 300 divided by 4 is 75. And then our units are just the units on the top, the word per, and then the units on the bottom. So bricks per hour. I know nothing about masonry, so I have no idea if that's even the slightest bit realistic, but it works for us. Any questions? Is this making sense? Okay, so that'll do it for today.